Parabolic projectile motion. Parabolic projectile motion is when an object is shot out at a non-horizontal angle and travels in a parabolic path. If we take a look at an example, we can look at this image here to give us a visualization of what parabolic projectile motion would look like. As you can see, the object here is fired at a non-horizontal angle from the horizontal plane. We call this initial angle theta. Many objects and many real-world applications apply to parabolic projectile motion. Some of them off the top of my head are basketballs. If you shoot basketballs, basketballs would follow a parabolic path. Footballs, and basically any things that you can throw would qualify as parabolic projectile motion. In many of the problems that we'll encounter, we'll be talking about cannons. And if you imagine this being a cannonball being shot out of a cannon, the cannonball would basically follow a path very similar to this. And we can use the rules of parabolic projectile motion to model and to determine some of the features of these types of situations. So let's look at some of the characteristics of parabolic projectile motion. First of all, horizontal velocity. Not much to be said here. It remains constant throughout the object's fall. This is very important to remember. Vx, the horizontal velocity, does not change throughout the object's fall. In addition, the velocity vector, vertical velocity vector, I should say, this does not start at 0 meters per second. It is a non-zero number. It starts off with an actual value. This is very different from horizontal projectile motion, where the vertical velocity does start at 0. In addition, the magnitude of the vertical velocity decreases initially and then increases as gravity accelerates the object downward. So as you can see, if you think of this as being the first half of the object's flight, during this first half, the vertical velocity is decreasing. Now, if you think of this being the second half, so once it reaches its climax point here, you can think of the second half as the point where as the path where the vertical velocity starts to increase, the magnitude. Another two very important points. These are the two most important points related to parabolic projectile motion. Vy, the vertical velocity, equals 0 at the vertex, or the maximum height. So we consider this being the max height. This is the maximum height that the object reaches, and at this point, Vy equals 0. You can think of it as the vertical velocity as pausing, as reaching 0, reaching nothing at the very top of its path before it starts to increase again. All right, down here now, at the end of its path, so when it hits the ground, okay, we're going to label this hits ground. When the object hits the ground, let me make some room here, Vy is going to be the complete opposite of the initial vertical velocity. So whatever it started at here, okay, at the end of its path, its vertical velocity is going to be the exact opposite. So Vy is going to equal to negative V initial vertical velocity. That's very important to know. Okay, moving on to some important equations. So these equations are the exact same as the equations for horizontal projectile motion. Going through some of them again, we have vertical velocity equals the initial vertical velocity plus g times t. Horizontal displacement is dx equals the horizontal velocity, vx, times t. And then we have the vertical displacement formula, which is dy equals initial vertical velocity times t plus 1/2 gt squared. These are the exact same variables in the exact same equations. This is not going to change. The only important things to note are those two key points that I brought up earlier about the vertical velocity being 0 at the vertex and being the opposite of the initial vertical velocity at the end of its path. Three more important formulas here. Many of these problems are going to give us the initial, the velocity vector, and that's going to be equal to v sub 0. And then they're also going to give us the angle, okay, the angle of the trajectory. And that's going to be equal to theta. So when I talk about the angle of the trajectory, I'm talking about this right here, this being our angle. And then when I talk about the initial velocity vector, this is what I'm talking about here, the initial velocity vector. So with these two pieces of information, we can determine the horizontal velocity vector, the initial vertical velocity vector, and we can do those using trig functions. So the horizontal velocity vector is going to be equal to v times cos theta. The initial vertical velocity vector is going to be equal to v times sine theta. And then finally, at any point in the object's path, we can determine the angle theta by determining Vy and Vx and finding the inverse tangent of this proportion.